referencing back to what we did last Friday. And if you can look on this handout, you got this kind of got a spiral holding it together. On page 63 at first. Okay, here we have a set, I think, of 10 subjects, 10 children, whatever it is, students, and we have a scale with 8 items, okay? And this could be like a pilot study. It could be like a pilot study. And they are assigning it binary. Come on in. This would be like and it was a binary response, either true, false, right, wrong, yes, no, something like this. Now, it could have been a Likert scale. You can use a Likert scale, but I used this. These are contrived data, okay, for this book or paper manuscript. But, and if you turn over to the next page, on the top of page 64, with those 8 items, okay, we got a Cronbach's alpha of 0.66, which means 66% of the total variance that you're getting, where they have high scores, average scores, or low scores, of that total variance is true or reliable or intrinsic to the individuals being observed, students, patients, clients, whoever it is. And 34% of us due to content sampling with 8 items. Now, you remember last week, the reason I'm pointing this out is somebody asked me about, are there any formulas for estimating how many items you need to have a certain reliability coefficient? So if we turn over to page 65, there's something called Spearman-Brown's prophecy formula. Okay, and with their formula, you can see here at the top, and Q is the number of times you've increased the length, because given everything else equal, the more items, the more observations you have, the greater will be your true variance or reliable variance, and the smaller will be your measurement error. Given everything else equal, the fewer the items you have, okay, the fewer the observations you have, your true variance is going to decrease, and your measurement error is going to increase. And I'll show you how this works just a little bit. So if Q became 2, with 8 items, you see it was 0.66, as you saw on page 63 and 64. However, if we make it twice as long, in other words, we increase it to 16 items, given everything else equal. Now, that has to do with item distribution that we talked about last week and item discrimination index, okay? It involves both, okay? The item distributions and the item discrimination, that's what they mean by it is quote-unquote equal. But you see the reliability coefficient goes up to a 0.80. And that means 80% of your total variance is true, and only 20% is in fact what? Due to measurement error. So that's probably worth it. It's probably worth it to go ahead and try to increase the items from 8 to 16. Now then, you go back out to Q, where under Q it says 3, we're going up to 24 items. And now we get up to 0.85. The Spearman-Brown's prophecy is 0.85. 85% is true, 15% is due to measurement error. And if we go back where the Q is 4, you see you go up to 32 items. But your Cronbach's alpha goes up to 0.89, and 11% is due to measurement error. So your measurement error is decreasing. And if you made it 5 times as long, 40 items, you get to a 0.91. And you see now you'll notice there's diminishing returns. It's not as increasing as much. There's diminishing returns. And you have to take, because especially if it's a survey you're sending out, you don't want the people to be frustrated, okay? Oh, by the way, I was on a doctoral dissertation committee yesterday in another college, not in this college. And some of the issues we talked about last week, we were discussing. And also, but then this person, he or she was going to be collecting data in the hospitals, I think in the schools and some other businesses where they have phone banks or something like that. And then she was going to do it through email, okay? Collect the data through email. Well, I found out that there are a lot of people all over the world, I guess, but all over wherever you're sending those emails out to, that because they pay them, they give them a little money, okay, $1 to $5 for filling the survey out, okay. What they do is sit at home all day long and scan looking for surveys to fill out so they can get some money. That's how they make a living. Solid research, right?
Yeah. We're going to have some real results.
Anyway, so now, the point now, look at just below that 5, the Q of 5, I went to a Q of 0.5, meaning making it half as long, so we dropped from 8 items, the original. So always going back to the original 8. Go to 4 items, and you see your Chromebus alpha drops to a 0.50, and your measurement error goes to 50% of your total variance is in fact due to content sampling or being a little bit lucky or unlucky, as we talked about last week. If you dropped it down to just a 1/4, 0.25, 2 items, your Chromebus alpha would be a 0.33, and you'd only have 33% of your total variance true or reliable, and 67% would be due to content sampling, being a little bit lucky or unlucky. See, so it's not spread out. If you have 19 or 20 items, you're spreading it out a little bit, that being lucky or unlucky. But if there's only 2 items or 3 items, I know both those items, perfect score. If those 2 items I don't know, boom, got a 0. So, and that's one reason that you've seen these mastery tests and criterion reference scales that they use in the schools a lot. The reliability is a disaster on them because they only have, if the child can get like 3 out of 4 items, he's ready for the next objective. But the reliability, if those are the items he knows or she knows, boom, they go. If they don't, boom, they don't. So the reliability is highly questionable. But I thought I would point this out. You can use the Spearman-Brown prophecy zones. You did a pilot study, and then you could, if you only had 8 items in this case, but you might have more, then you could estimate, given everything else equal. Now that means the item distribution, the variance, and the item discrimination indexes, because the discrimination indexes, we pointed out last week, if the discrimination indexes are between a minus 0.30 and a positive 0.30, and you leave that item in, it's going to attenuate, reduce your reliability coefficient because you're entering a lot of noise. Now, of course, on the item distribution, you're looking at how well does that item discriminate between and among individuals in terms of anxiety or stress or depression or whatever, reading achievement, whatever it is. And then the item discrimination index tells you how well that given item discriminates on that scale. Okay, it's on that scale. But anyway, I just thought I'd point this out before we got started with today because it references back to what we covered last week. Okay, now we're going to take a data set, and I'm going to have to go to the ETRC on here on the computer. We'll be going to something different than this, okay, the ETRC. But if you see this data set, it should have been in your folder. And this is just a short description of a data set. 369 women were administered 44 item inventory scale. Now these were women that were actually in like executive positions or administrative positions in schools, hospitals, companies, corporations, etc. And these 44 items, a lot of them were temperament scale items, as you can see. But we know, as we talked about last week, if your items, you have 44 items, you're not measuring 44 different phenomena. You know, you might be measuring 3, 4, 5 phenomena, 6 phenomena, but not 44. Okay? Because if 2 items are highly correlated, they're tapping and extracting the same underlying latent phenomenon. It doesn't mean that one causes the other one. It just means the common overlapping, the variance is so high. So they're tapping and extracting the same underlying phenomenon. So we're going to be using a method called factor analysis to do a data reduction, variable reduction, item reduction, whatever it is, to find the underlying dimensions. Now I've used this data set before. And it's not the easiest to work with, okay? But we can learn from it, okay? We can learn from it. And when we get over to it, we will be looking at this sheet here. Do you have a sheet like this? I don't know if this is the best time to talk about this. It should be in your folder. It should be a sheet. It shows before rotation and after rotation. This, I just made this up to illustrate it, yeah. Okay, over here are the items. Do you see these items? You got V1 all the way, 9 items altogether. Again, this one will have 44. Now in this case, this here before rotation is principal components analysis. Now principal components will tell us how much of the total variance is explained and the method we're using, depending on the eigenvalue set, etc. Okay, but that's its only use. Because look here, you'll see here like with item 1, it says it loads medium, medium, and low. Now, we don't consider an item loads on F1, F2, F3 a factor unless it has a 0.40 or greater. Or sometimes we go to a 0.45 or greater. If it's less than that, we say it's not loading on that factor. A high loading would be like 0.60, 0.70, 0.65. 0.82, that would be, those would be strong loadings, high loadings. Okay, a low loading would be like 0.30, 0.22, something like that, doesn't load. Well, you look at item 2. It loads on the first factor medium, which might be like a 0.57 or something like that, and on the second factor a 0.58. And look at the third factor, it loads what, say 68 or 78 or something like that, or 0.80. So it's medium. We don't want that because it's ambiguous. It's ambiguous. We want a simple structure. We say in this case it's cross-loading. It's loading on all 3 factors, so it makes no sense. We couldn't use that item. But we have another way of handling it before we do something like that. We go over here and we use Varimax rotations or type of rotations. Varimax, quarter max, equal max, something like that. Now, often we use Varimax because that gives you independent orthogonal factors. You don't want them. You try to get, say, items 4, 11, 17, 18, 22, 31, 32, all load on the first factor. You don't want them loaded on the second or third factor or fourth factor. You want it pure. It's easier to interpret. And we always, in psychometrics, want, in terms of validity, we want it to be pure. We think it's easier to interpret that way, to understand what it is. It's not measured, like if you build a test to measure math, you don't want it measuring reading, every other thing in town, okay? Depression, anxiety, stress. You want it measuring math. Same thing with reading. You don't want to, because it's difficult to interpret. You want it pure as possible. And that's what we're going to be trying to do with those factors, to get them as pure as possible. Then after we able to do, so we'll be using Varimax rotations, which maximizes the loading on the columns or the items, the variables. Quarter max would maximize on the rows, which would, in this case wouldn't make any sense. And then equal max will maximize on both of them, would maximize on both of them. The second one is quarter max. Quarter max. That maximizes on the rows. And equal max maximize on the rows and columns. Rarely will use that because it will yield non-orthogonal factors. And again, you got the reason you're doing it is to find out, to get reduce the data and get some purity. But there are times when you have to use that. I have had to use it before. Rotations. In this case here, you'll notice when we used the principal components before rotation, we were explaining 78% of the total variance in the data structure on all 9 items, because we only have 9 items here. And after the Varimax rotations, we're still explaining 78%. But let's look here at the Varimax rotations. Okay, look at item number 1. Do you see item 1 had a medium, medium, and then low loading? Now after rotations, it's got a high, low, low. So that item 1 is loading really purely on factor 1. Okay, and then we can see on, was item 2 here, it's still a little bit messed up here. It's got medium, medium, and then high on with the principal components, but with Varimax rotation, it's got low, medium, and high. But see, it's still cross-loading on the second and third factor. So this may be an item you want to throw out, because you don't want that in there, because it makes it much more difficult to interpret. Again, as I said, you want it pure as possible, or whatever it is that you're measuring. I think here's number 7. Look at number 7. It was medium, medium, and then low. But after the Varimax rotations, we had low, high, low. Okay, so we got a much better fit there. So that item 7 clearly loads on factor 2 and not factor 1 or factor 3. And that's what we're striving for. That's what we'll be striving for. So I'm just trying to give you a little, you wonder why we're doing such and such on the computer? Well, that's the reason we're doing such and such on the computer. Okay, and then also, we could also look at the item distributions before. Now, remember we talked about the item distributions last week and the discrimination indexes and that? If the items are not distributed, okay, normally, okay, and you're trying to what you're trying to do on that given item is maximize the detection of individual differences that exist. The reason you're measuring and observing the patients, the clients, the subjects, the cases, the children, whoever it is because you think they're not all exactly the same in terms of stress, in terms of anxiety, in terms of math achievement, reading achievement, depression, whatever it might be. You don't think they're all the same. That's why. So that's the reason you're measuring them. So as we said last week, you like to have your data normally distributed, continuously valued, and normally distributed. Now, it's very difficult to get that, okay, completely. I showed you an example last week where we also selected the items, so we didn't get a Gaussian. Remember, we got a bimodal. You can deliberately select items and produce by any shape of distribution you want, okay? But the reason we try to get the Gaussian on each item as close as possible, and then when you aggregate all of them, you'll have a Gaussian. And yesterday came up in that doctoral dissertation defense, why do you want to have a Gaussian or normal distribution? You're maximizing your detection of individual differences, A. B, your true variance, your reliable variance, and your measurement error variance won't be correlated. If it's skewed, then your measurement error, your true variance, your reliable variance, and your measurement error variance will be correlated. And you got tons of trouble. You just might as well go and put this basura, junk, trash. Go to the trash barrel because you've got real troubles. And I'm going to just shift gears. In data analysis, statistical analysis, we assume normality of distribution. Okay, like in analysis of variance, regression analysis, etc. I want to explain to you why. Because I was on doctoral dissertations at UT Austin several times. This one professor in the committee would always ask the student, how come you're assuming normality distribution? Making the student nervous, okay? I knew that he or she did not have a clue why they were asking what the question was. Okay. The reason for you assume normality is not because you like symmetry in life. It's because you don't, your treatment variance, your between group variance, and your within group variance, your error term, your denominator, if it's normally distributed, will not be correlated. Okay? In regression analysis, which is mathematics is the same in general linear model, is your sums of squares due to regression and your sums of squares due to residual won't be correlated. If they're skewed, then they'll be correlated and you're going to increase your risks of a type 1 error, alpha error. Now, kurtosis errors, deviations in terms of the height of the distribution, leptokurtic, platykurtic, won't impact type 1 error, alpha error as greatly. But skewness will. Skewness will have a greater impact. So that's the reason you're assuming normality of distribution, is so that your true variance in psychometric theory, true variance and measurement error variance are not correlated. In data analysis, you're analyzing phenomenon, analysis, variance, regression analysis, whatever it might be, path analysis. The reason you're assuming that is because you don't want your treatment variance or your sums of squares due to whatever phenomenon correlated with the error term. Okay, so if somebody asks you, now you know the answer. The doctoral student yesterday knew the answer. That's good. Okay. So with that, I'm going to see if now, with that introduction, then give you a conceptual framework. What we'll do then is we'll click on and get some data. Now we're going to, Juan, I'm going to go to the ETRC, okay? You have to click on the online media. When you get to the ETRC, it's online media, and
It'll be right here.
Juan has been
Online
fortunate enough
media.
to store a lot of data for me on the computer.
You
So
click here and scroll down to the listing for Dr. Carlson's resources. It'll be the first one, number 8. You click on that, it'll expand. You scroll down, it's going to be number 10. If you click
Factor
on
analysis.
Factor analysis, it'll prompt you to save a zip file. If you can save it, you can save it to the desktop.
We want to open it, right?
Yes. You can click on Open Folder and right-click on the file, extract all,
Oh,
and just extract. And you can double-click on the file to open it.
now, factor analysis is really just a descriptive procedure. You're looking at construct or theoretical validity. It's actually still in the area of psychometrics. We're not really trying to analyze phenomena yet. Factor analysis is widely used in all fields and all disciplines. Charles Spearman, the Spearman-Brown, Charles Spearman developed the two-factor theory back in the early 1900s. Then Thurstone, L.L. Thurstone, at the University of Chicago, developed it further, then Harmon, etc. But it is used in biology, medicine, linguistics, psychology, physiology, nursing, medicine. Is widely used in factor analysis. But it's essentially a descriptive. It is a way of describing what you're doing, but in this case we're using it for in terms of the underlying theoretical constructs. Okay. I'm going to sit down now so I can work here, but you still can see. Okay. I'm going to go here to analyze. Now, we could do some descriptives here and go like this and go over to explore and look at the items with the box whisker plot, stem leaf, and things like that to see what each item is doing in terms of its distribution, do you see? And the amount of variance it's yielding, if any, and et cetera. And is it skewed or leptokurtic and all that business, like we were talking about last week on each item. But I don't want to get into that too much because maybe we could do one item. Because I want you to be able to print out. And if we did all 44 of us, the print, man, we'd use all the paper in the world here. So we maybe want to look at one item if you wanted to look at one item. And do an explore on that and see what it looks like. Okay, well, we'll go ahead and do that. Okay, I'm clicking on explore. And now this, how do you see yourself? Let me see here. The items were worded as how do you see this trait or this item as to you. You never, or never is 1, and all the way to 7 is always. Okay, always helpful or never helpful. Okay, if you see yourself in terms of that item. So I can take and I'll click on helpful. Okay, and I'm going to move it in here, dependent variable list like this, and then a statistics like this here, and descriptive. I don't want to do anything other than that with this. So I'm going to leave it. Plots. Now, with this one here, I am going to, I want to give a histogram to it. I'm getting the stem leaf. And then here it says normality plots with tests. And SPSS has two tests for normality of distribution. One is the Kolmogorov one sample. Now they say KS, Kolmogorov-Smirnov. That's not correct. Kolmogorov developed the one sample in 1933, and it wasn't until 1936 Smirnov and Kolmogorov developed the two sample together. They did a little refinement in 36, but the Kolmogorov is the most powerful test for normality of distribution that we have. At 30 degrees of freedom, it has extreme power. As a matter of fact, when you get up around 90 subjects, it's going to reject, or even 60 subjects. And it will detect any, if I had more time, maybe I'd show you what it looks like, but it will detect any skewness or kurtosis deviation from normality. I think I'll go ahead and plot it here on the board. Now we're going to accumulate cumulative proportion of area. Yeah. So it's going to be like 0.10, 0.20, 0.30, 0.40, 0.50, 0.60, 0.70, 0.80, 0.90, and 0.9999999 because the distribution is asymptotic and never touches the bottom axis. Here might be low scores here. Okay, here are average scores here, and here are high scores over here. So let's play like we had the theoretical mathematical distribution. Let's play like we have the theoretical Gaussian. Did I put the Gaussian distribution in your file, in your folders? Okay. What we're going to be doing, I can put the Gaussian up here so you can see. Play like this is a Gaussian. Well, it's not at all. I should be able to do this. I've been doing this for 4,000 years. Okay. So the mean might be right, approximately right here, okay? And so this is a theoretical mathematical distribution, which represents the rationalist position of epistemology, Plato. It's a pure theoretical mathematical distribution, probability distribution. That's what it is. And what the Kolmogorov one sample case is it takes and accumulates the area from low to high. From low to high. So you can see down here, the area is very thin, so you're not going to accumulate much at all at first. But up here, we're going to start really accumulating a lot of area when we get higher. So what's going to happen here is a distribution is going to look like this. We're actually going to be accumulating area, increasing at an increasing rate. And then, when we go beyond this, it's going to start going like this. So this would weigh that if we accumulate a theoretical mathematical distribution, and that's the rationalist position, and that's all you're doing in statistics is comparing your observed, the empirical Aristotle, with a theoretical mathematical Plato. And so you take your observed data, your observed distribution, and it may look something like this when you plot it against it. Okay? And it's going to take, and it gives a d value like this, and it will detect any skewness or kurtosis deviation from normality. That's a Kolmogorov one sample K test, and SPSS has that on there. It also has on there the Wilk-Shapiro test for normality. And the Wilk-Shapiro will go down and test for normality of distribution with 5 degrees of freedom. That's incredible. That's incredible. But anyway, so this will detect any skewness or kurtosis deviation from normality. But I said at 30 degrees of freedom, it has the most powerful test for normality we have. It's going to reject on you. And you get up around 90 subjects or even 60 subjects, it's going to show all the time. Then you need to go look at the skewness and kurtosis indexes. So, okay, I'm going to click on continue. Oh, here, I want to do both tests. See, normality of plots with tests. I clicked here, stem leaf. Now we can do histogram too, I don't know. Okay, continue. Then options, I don't care about any of the options, so just get rid of that one. And now I'm going to click on OK. Now we only did one. We're not doing all 44 items. I just picked out the first item. Now remember the scale runs from 1 to 7. The Likert scale that the people responded to, all the subjects, the 369 women in leadership positions, administrative positions in schools, hospitals, corporations, etc. Okay, now we can see here the mean is 6.5, right? Look at that. And here is the confidence intervals that cover it. Here's your standard error. And what it does, it goes in and actually gets the t-value, the critical t-value, given the degrees of freedom, and multiply out with a, well, if you had an infinite, it would be 1.96. This the trim mean, okay, what it's doing is taking the extreme, now this is probably not all that useful when we just got a scale of 1 to 7, but when you're analyzing your phenomena, it takes the extreme higher 5% and the extreme lower 5% in the distribution, and that variable truncates it and recalculates the mean. And that way you can tell if the extreme scores are having a big impact, because if the recalculated one and the one where you have truncated, trimmed the extreme up 5% or lower for 5% is about the same, okay, then you probably don't have any extreme scores. That's John Wilder, Tukey. John Wilder. All this exploratory data analysis is John Tukey. Now you see the median and the mean are pretty close. And here's the variance and the standard deviation. Now here's the skewness index. Okay, it's negatively skewed, and we can tell that with a mean of 5, it's going to be negatively skewed. So that item, the first item, helpful, the data, and I hear 6 and 7, etc. The data has a pretty strong negative skew to it, you see. Now again, each item, you're not dependent on one item. You got 44 items. So they don't have to be perfectly Gaussian. You can still use it. But this is going to impact your discrimination index we talked about, your Cronbach's alpha, your reliability coefficient, and if it loads or not on anything. If everybody marked a 6 and nobody marked a 7, nobody marked a 5, a 4, a 3, a 2, or a 1, the item it would eliminate itself. It wouldn't load on anything, you see. You have nonsense. You never interpret you see these skewness indexes? See that standard error beside it? It's a 1.127, I think. I don't have my glasses on. And you see the skewness index? Okay, this significantly. You can do it like roughly a t-test with that. You never interpret the skewness index or the kurtosis index by themselves. You always interpret in light of their standard error. So roughly it's like a one sample case t-test. The skewness index was a minus 1 point something. Can you help me? 4? What, 3?
3.5.
And
Oh yeah, there's a 1 before the, it's 1.135.
1.135.
Sorry.
Oh, okay. Negative though, right?
Yes.
Yeah.
1.135.
Okay, the standard error right to the right of it is what? 0.12 or something?
1.127.
Okay, well I should use that green because I always want the error term to be in green. A 0.127. And see if you divide that in there, and it's going to show significance. If it'd be greater than 1.96, okay, or 2.58, which it will be, it significantly has a negative distribution. You can do the same thing with the kurtosis. What was this was skewness here, this was skewness here. and the kurtosis one, that has to do with the height or the density of the distribution like that, or if it's platykurtic like this. Okay, with the kurtosis, sounds like a foot disease, doesn't it? I know. What was the value for kurtosis?
1.703.
Positive, right?
Yes.
Right.
1.703.
703.
703.
I'm sorry, my hearing is not good at all. And the error term, the standard error for the kurtosis?
0.253.
Okay. And likewise, you're going to have, it's going to show this. Now, when it's positive like this, that means it's lepto. When it's positive, it means it's leptokurtic. Leptokurtic, if it's positive. If it's negative, that means it's platykurtic. Means you have a lot of biret scattered, you see. If it's close to 0, that means the ordinate is like you'd expect for the Gaussian distribution, the normal curve. If it's close to 0. So you want them to be close to 0 as possible, both ways. You want it close to 0 as possible. You'll never, in nature, find, if you do, somebody made up his data, okay? Remember I told you about Cyril Burt at the University of London. That's how they caught him. Okay. So now we can go down here and test for, now see the Kolmogorov, they say Kolmogorov Smirnov here. It's not. It's Kolmogorov one sample, but that's not a substantive error. That's just a typo error, okay, not knowing the history of statistics. But see this is significance, that's the probability, that's the p-value. That you don't want that to be less than 0.01 or 0.05. On your assumptions, you want to fail to reject. You want to fail to reject. And so both with Shapiro-Wilk and with the Kolmogorov, we do not have normality of distribution. We can scroll on down here a little bit and we can look at it more. You can see now the negative skew to it. Now here's the stem, and what we're doing here is how many 3s did you have? The width is, the stem width is 1. So we had a 3, we had, let's see, stem 1. Case, each leaf has 2 cases, so there's 6 3s. There's 67 5s, 130 6s, 147 7s. The stem leaf again plot was developed by John Wilder Tukey. And here, how could this be? Oh, okay. See the scores over here, 1 through 7? Subject we can identify. This is the box whisker plot. This line right here is the median. This is the upper. This is the second quartile. This is the first quartile. And this is approximately 2 standard deviations below the mean. This here whisker here. And you see this here 126? We can go in our data, and if we find subject 126, we're going to see they have a score of 1. And there was only one person evidently that had that score. So you can go in and detect outliers that way, extreme values, outliers. Now how you handle the outliers is another thing, and that's another whole class, okay. But now let's go back and get to the factor analysis. But again, I just want to show you this because last week we talked about how the item was distributing. And we'll see what happens with helpful when we do factor analysis. So we're going to go back to analyze again. You ever see what I'm at? And I'm going to go down to dimension reduction. And then we're going over to factor. Now what we're going to do is I'm going to enter all of them. So if I click here, and then I go all the way down, I should be able to, the last one, press on shift. Do you see they all highlighted at one time? I pressed on shift. I highlighted the first one, not subject, just the first item. The first one is subject. You don't have to put that one in. You want me to go back and do it again? Okay. Let's go ahead and get rid of this here. Okay, we don't want to use the subject, but the first item that we're interested in is helpful. That's the one we just looked at in terms of explore data analysis. Now you can individually put them all in there. You can do like this, okay? Click on this little thing here, and it'll go in. But you'd have to do it 44 times. So I'm trying to show you can click on self-reliant would be the second item. I don't need it. And now I can go all the way down to the bottom here. And now I'm going to push on shift. You see the shift button? It says shift on it. Press on that, and then click on gentle. Do you see what happened? And now then, I click on this arrow here, and it all goes in. Do you see? I already put helpful in there. So all 44 are in there. Now we can look at descriptives. Are we interested in that? I'm not really interested in any of the descriptives, okay? That means I already have that with exploratory data analysis. But extractions, okay. Again, I'm just going to use the initial solution here for the factor analysis, so I'm going to close this. Rotations. I'm going to click on Verimax. Now you notice here it says a maximum of for convergence. It's inverting and rotating the matrices, dividing and rotating the matrices, 25. Sometimes if you're having difficulty getting at the factor, you'll have to go up and go up to, I've had to go up sometimes even 100 iterations, okay? The number of iterations it'll go through before you can get it to converge, sometimes even more. Especially if you got a lot of measurement area in there and the distributions are all not even coming close to normality at all, you'll have to do that. The Verimax, okay. Let me see here. I gotta go back and do something else here. Let me see. Options. I don't care any of that. Continue. Extractions. I should have clicked on that first. Okay. Okay. You see, it's doing principal components here. By default, it's going to do that. I'm going to click. Did you see where I got this? Let me go back. Extractions. Click on extractions right below descriptives. Now I'm going to do unrotated factor. That's principal components. You see up there? And then I'm going to do a scree plot. The scree plot will help us interpret how many factors we should retain. There are many decision points that we'll be using. We're going to start off with the eigenvalues of greater than 1. Okay, but anything lower than 1, it's not going to be loading. So then I'm going to click on continue, and again it's going to 25 iterations. I may have to change it. I forgot. It's been a while since I ran this data set. And now I'm going to click on OK. Okay, now here are the commonalities. There's one over there loading, and that's partly important in interpreting. But the first one we come down here is variance explained. Okay, now you see here's the initial eigenvalue, anything eigenvalue greater than 1. So we're getting 12 factors out of 44 items. We got a problem. We got too many factors, okay? We got too many factors, which means we're going to have to move our eigenvalue up to, say, 1.5. But I'm going to leave it at this for right now, so you can see, when we go on down, I'll show you the one we actually interpret.
How to decide it's too many factors or
Well, we got 44 items, and how many did it say here? 12. Divide 12 into 44. On average, how many items would be loading on each factor? See, 4? No, not quite 4. If you don't have more than 2 items loading on a factor, you don't have a factor. If you're just one item loading, you don't have a factor. So and in order to build a scale, and then what I'd like to do with this is after we do the factor analysis, is do a profile analysis, because the factor analysis is not going to really analyze the phenomenon. So then we're going to transform all of the factors we end up with, 3 or 4 or 5, how many, into common metrics, common calibrations, so we can do a profile analysis to see which the women that have the leadership positions in administration, hospitals, schools, or agencies, we can actually look at their profile. We can actually look at their profile. Because the factor, you say, well, the first factor is explaining more variance than the second. It's more important. But that doesn't tell you about the phenomenon. Also, after factor analysis, you may want to take those factors and use in a regression analysis. In other words, if we come up with 5 factors, I'm just using an example, we may want to look at, and one of them has these different temperament, one has to be an assertive, interpersonal skills, or whatever they are here. And then salary. We may want to see how much of the variance in salary have high salaries, average salaries, and low salaries here. How much of this variance in salary is accounted for, explained by their temperament, how much they're getting paid. And you're regressing salary on these 5 factors. And you can use, that's one use for using it. What we're going to use it for is transform into common metrics, and we'll be able to look at the profile. We'll be able to find the mean for all the factors, but also to see if they peak on one and then lower on another, etc. This is factor 1, factor 2, factor 3, factor 4, factor 5, factor 6. I got 6 factors now, but you have to transform into common metrics before you can do profile analysis. But now when you do this, you're actually analyzing the phenomenon in nature. Or this, you're actually asking a question, analyzing the phenomenon. Up here, we're just still doing psychometric. We're looking at construct validity. So let's go on down. And again now, you'll notice we got how much variance explained. Cumulative, 61% of the variance is explained, which is reasonable. With the principal components. Okay, now we're going to go on down to Verimax, and that's what we're going to do. Here's the scree plot. Now we set the eigenvalue at 1. See right here? And it will give you back, principal components, we set the eigenvalue so we controlled it. But it'll give you back, 44 factors or 43 factors. It'll give you back 44 of them. It didn't put 44 out here, but there's 44. And here's 1. Okay, here's the eigenvalue 1. We go across like this, and see where that elbow kind of turns into an elbow? That helps us to interpret how many we're going to actually retain. But if we move it up here to 1.5, you see, we'll only have 1, 2, 3, 4, 5, maybe 6 factors at most. Okay. The scree plot comes from, you've seen on volcanoes, like volcanoes, the scree comes down the side after they have an explosion like that. Well, if in a bivariate distribution, if the coefficient is really high, the regression or correlation coefficient is very high, you have a high it's a negative skewed, and it comes up like this here, really high, and it looks like scree coming off, okay? And that's the reason with the normal curve, do you see? On the normal curve, the volcano is going up and it's coming off nice and smoothly. Scree plot. I don't know who developed that thing. Okay, this is the one we're going to interpret. Rotated component matrices, okay? Rotated component matrices. Now, unfortunately here, we have got 12 factors, do you see? Clear over here. And this is going to be, all night interpreting this. But what I want to show you here, See this, this first factor, helpful doesn't load at all. You want to, and this time, right now, initially, I'm going to start with 0.40 or higher. I can count it as a loading. That's 0.20. Then defends beliefs, 0.32. Yielding, negative. Now, you don't care. Then if the loading is negative, that's fine, as long as it's greater than a negative 0.40. Okay, assertive, okay, that's a 0.74. That loads on the first factor. The next one, strong personality, loads on the what? First factor. Forceful, 0.78, 0.79, first factor. Affectionate, or affective, or I don't know how to affect. That is 0.788. And now I also should be going across over here. See it loads, see these 0.7s? Okay, it loads, doesn't load on any of the other what? Factors, and that's what you're wanting. Leadership ability, 0.60, etc. But this is how we interpret it, like this. Okay, I'm going to go back and rerun this, but dominant, masculine, willing to take a stand. Let's see. Act as a leader, loads on factor 1, etc. But now we're going to go back and I'm going to change the eigenvalue to 1.5. So I'm going to go back to the analysis again. I'm going to go back here to dimension reduction factor analysis. It's exploratory. You have exploratory and confirmatory. In psychometric theory and measurement scaling, you don't test hypotheses, only with confirmatory factor analysis. Otherwise, there's in psychometric theory, measurement scaling, we never test hypotheses like we're trying to analyze phenomena. Okay, I'm going to change this extractions. I'm going to make this a 1.5. Now we'll see what happens. 1.5. So I'm going to click on continue. And now I'm going to click on OK because I'm going to leave everything else the same. There should be a scree plot, etc. Now notice we only got what? 5. We cut out 7 factors. But we've given up something. For parsimony, we have given up, we're now only explaining 43% of the total variance. Now this is principal components. Only thing you use principal components for is to find out the total amount of variance to explain, but you can also see that when you do the Varimax rotations. But well, the scree plot. Let me get back to the scree plot. I'm sorry. Okay, 1.5. See right here? That'd be someplace, I guess, right here. I don't know. And how many factors did we say we had? 5? 5, right? So 1, 2, 3, 4, 5. So it's evidently right here is 1.5. I cut it off. But that elbow turns there, so that's basically you would want to do that. Okay. Now this is easier to work with. See, this is going to be easier. We don't have 12. We only have what? 5. So now let's look at this helpful thing. Look at what it helped the helpful. It did not load on. It didn't load on any of the 5 factors. ¿Por qué? This may be one reason. Or even if it had been normal, you may not, it's just not measuring, tapping, extracting any one of those 5 underlying dimensions. It could have been even a Gaussian, it's still not. But this is, will preclude it from loading on anything. Okay, let's see. La self-reliant. it loads on factor 4. Do you see factor 4 over here? It's a 0.528, a 0.53. You see that? Okay, so self-reliant loads on factor 4. Okay, defends beliefs. Okay, it loads on factor 1, a 0.49 or 0.485, 0.49. Yielding does not load on anything, right? So both items 1 and 2, 3, 4, yielding, will have to be eliminated. That's the reason you start off with the item pool much larger than you're initially than what you'll end up with. If you start off with very few items, you're probably digging yourself in a big hole. And also you can lose items because of the distributions and item discrimination. But actually factor analysis will take them out anyway. Okay, let's look at cheerful. Cheerful loads on what? 3. And what's good about cheerful, it does not load on 1, it doesn't load on 2, it does not load on 4, and it does not load on 5. And that's what you call a simple structure. And you want a simple structure. In other words, whatever this factor 3 is, because the computer won't tell you what factor 3 is. You're going to have to figure that out. Okay? You're going to look for the theme that runs through it. But it's pure. And also was over here with defends beliefs. Well, self-reliant. See, self-reliant was a 0.52 here, but it didn't load on any of the other factors. We're going to have some items down here that's loaded on 2 or 3 of the factors. It's got to go too. That item's got to get out of there. We can't use it. Because it's ambiguous. We call it cross-loading. Now, here we go, independent, meta. Independent. Factor 1, 0.43, but what? Factor 4, 0.51. See the problema? It's not clear. It's loading on factor 1 and on factor 4. What I do when I print this out, I go through with a red pen, because I like red pens, and I circle the ones on the factors that are loading 0.40 or greater. Now, there's a way you can do this with a computer, but I'm not going to teach you this right now, where you can suppress any of them that are not 0.40. You can suppress them so it doesn't show them. But I think initially you want to do this, and also when you're learning it. Okay. Okay, so independence, cross-loading. It's got to go. Athletic. Doesn't really load on anything, right? How about shy? Shy does load on factor 1. And it does load on factor 2, 3, 4, and 5. Then we have assertive, loads on factor 1, like it did before. Strong personality on factor 1. Forceful on factor 1. And let me see. Leadership ability. But let's go back and see if there's any cross-loadings here. Nope, see? Wow. Oh no, affectionate, if that's what it is, loads on what? Factor 3. And that also, now look at the other one up here that loaded on factor 3 was what? Cheerful. Okay. So whatever they're measuring common phenomenon. Okay, then we go down here to find some others. Okay, sensitivity loads on factor what? 2. And doesn't load on 1, 3, 4, or 5. So we're getting closer to a simple structure. But if we go back up and look at just the principal components, it won't give you this. But the Varamax rotations did this. Understanding loads on what? Factor what? 2. What other ones loaded on factor 2? Nothing? That's the first one to load on factor 2, right? Oh, sensitive, yeah. Sensitive, understanding, compassionate. Loads on factor 2. Okay, let's see which one other ones. Now here, look at it, makes decisions easily. Look at the problem with it. It loads on factor 1 and factor 4. It's ambiguous. It's going to have to go. I'll have to cross it out.
When you say cross it out, do you mean like take it off the survey that you're giving? Because this is for a pilot study, right? Or no?
Well, I don't know where I got these data. Somebody just mailed it, sent them to me. But you cross it out, you would delete that item. You wouldn't use it in your analysis. You wouldn't use it in the regression analysis, trying to see whether they had high salaries, average salaries, or low salaries. You don't want that item in there on that factor. It's going to mess up everything. You want to try to get it as pure as possible. If you're like, that's what bothers me on written qualifying exams or written comps. They say, well, I didn't like their grammar, okay, or I didn't like their spelling, or I didn't like their commas, okay, blah, 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 blah. That's fine. You give a score for that, but their knowledge about whatever the phenomenon is, you give them another score. Keep them separate. You don't mix them together. If you want to grade them for the grammar and all that, you put that over here, and then do they know the subject matter, the content over here? You don't mix them up like that. Okay, that's basically what you're doing. You're trying to get something pure. It's easier to interpret. And if it's ambiguous, and then likewise, this here wouldn't make any sense either. It's going to mess up everything because it's loading on one or two factors. We call it cross-loading. But you can call it whatever you want to. But that's what it is. If it's loading on more than one, 2 or more, then you can't. And then there's some that, like we looked at, didn't load on anything. But it's probably in part due to the item distribution. It didn't load on anything. I think that's what we have, Julissa, with that there. Academic attitudes and interest inventory. The distributions are all messed up. So makes decisions easily. Self-sufficient loads on factor what? 4? Clearly. Dominant on factor 1. Willing to take a stand, factor 1. So you can see factor 1 has had what? Pretty strong temperament qualities. I think factor 3 was what? Sensitive? Or something like that. No. Factor 2 is what? Compassionate, understanding, eager to soothe hurt feelings. All understanding, compassionate, and eager to soothe what? Hurt feelings. Also, you might want to find out, see, you could do this here also looking at selecting counselors. Shh. Over here, what is this? Makes decisions easily, self-sufficient, and conscientious. They seem to be loading over here, and they're not loading on other ones. Okay, should we try to print this out? I don't want to print all the other stuff. We can just print this one. Because what you could do then for next Friday is we could be circling them. You could be circling them then and look at the themes, and then we could do the profile analysis. I'll show you how to do profile analysis. But in profile analysis, we're going to have to transform them all into common metrics or common calibrations. In regression, no, we can just enter the aggregate the factor scores for that factor and enter them in as a variable, as an independent variable or predictor variable. We'll have 5, in this case we'd have 5 predictors, you see, or independent variables. 5 predictor or independent variables. And we'll have these 5 factors that we obtained here. Now, it'll only be the items that load on that factor, you see. And what we'll be doing here with multiple regression analysis, got 1, 2, 3, 4, and 5, is we're going to see how much of the variance in salary, where they have high salaries, average salaries, or low salaries, is accounted for or explained by each one of these factors. And so that's what you'd be doing with regression analysis. Here, you'd be able to look at the 369 women in leadership positions and look at the profile. Because this looking at the factors doesn't tell you the amounts of whatever those attributes are. And you have to do profile analysis to do that. Because I can't do all of now what we need to do. But I do want you to get the printout. The second one we did, you go through and circle all of those that are loading 0.40 or greater. And you're going to see a theme you should with this factor. Factor 1, factor 2, factor 3. You should see a theme that's running through it. Okay, and don't circle any of the items that don't load on anything. And if they cross-load, put a note beside it. This one cross-loads. This item cross-loads on 2 or more factors. And so we have to get rid of it. We can't use it in the analysis of the phenomenon. In the analysis of the phenomenon. Pardon?
These are women in leadership.
Yes, these are 369 women and either CEOs or in hospitals or in school districts, universities, etc. And then you can be looking at it, okay? And you'll be able to look up there when we set the eigenvalue at 1, and then the problem. We had 12 factors, okay? We moved it to an eigenvalue of 1.5, and we got 5 factors, which is reasonable for 44 items or 44 variables.
You don't need to print the one with the eigenvalue of 1, right? We just need the 1.5.
Yeah, but it might be for just teaching learning reasons, you might want to have it to look at. Yeah. But factor analysis is a very powerful tool, and the first articles were published in the journal Psychometrica and Biometrica, Psychometric and Biometrica. This is widely used. Yeah. See, what you can do is you can give a scale like to administrators, okay, and then to the staff in the schools. The administrators, you'll get a factor structure for the administrators, and you get a factor structure for the staff, okay, well, not staff, the teachers in the elementary, secondary, and compare the factor structures. You compare, or you could take secondary teachers and look at how they look at organizational climate, and then elementary teachers how they look at and then compare the factor structures where they're similar and where they're different. There's a lot of things. In fact, they've used this scale here, this 7-point scale they gave it to men in leadership positions, CEOs or in hospitals or schools, whatever. Also, and then they compared the factor structure on men compared to women. So there's lots of things you can do with factor analysis. It's very powerful. Yes, it's descriptive. It's not inferential. This is exploratory factor analysis. There's something called confirmatory, and there is hypothesis testing. But that's when you pretty much know what 4 factors should be. You say there should be 4 factors, given theory or whatever it is. Now, an interpretation of these, we may have some that load on a factor and don't load on the others, but they're not consistent with the theme running out, the theory. They have to be consistent with theory. And you'll have to eliminate them. They're not consistent with theory. I know one of the professors is working on an exam for trying to build a scale to give to counseling students before they enter the program or when they enter the program, and then at the end to see what's changing in terms of values, et cetera, et cetera, et cetera. Okay. Well, we had. Well, I was going to get to the problem with it, but we got lots of things that we have to work on that at, and then part of it was the item distributions, and so we had to go back and look at it several times, and I'm going to go back and redo it, try to do it again. Okay, but it's a tough ball game. So you cannot start off and say, well, I'm going to build a scale. You just make up a bunch of items. I'm measuring such and such. You can say that. You can say anything. Okay? You can declare the earth is flat too. Okay? But it's not, may not be what it is. I shared this with, did I share this with one area educational system around here? Years ago, they had given a 72-item survey out to all the educators from Brownsville through Laredo. And I went over there, and they were looking at each individual item, interpreting each individual item. Pobrecitos. First place, you don't have any reliability. One item will give you measurements we talked about last week. That item 11, that's measurement error. Okay. You might have 15, 20% true variance, and you got, 85, 80% measurement error, content sampling. Well, you noticed that on that page 65. On page 65, I showed you if you drop from 8 items to 4 items, what happened? And you drop from 8 items to 2 items. Can you imagine when you just go to 1 item? You got real troubles. Yeah, they need Spearman Brown prophecy formula to work with. That's the reason Dr. Rodriguez, Javier Rodriguez, when he first got here, he's in January or something, and all the faculty for tenure and promotion and everything were coming through, and all the departments reciting this item 11. He didn't tell me, but I've heard from 4 independent sources that he must have said, what is it with this item 11? Because he knew enough to realize that you just got 1 item in a 4-point scale, whatever, you got gobbledygook. Yep. You got nonsense. It was interesting. We pulled out item, was it number 1? Item, the first one, helpful. We looked at it and didn't load on anything either. Cross-validates what we were talking about. And you'll find that if they're loading on a factor, when you go to the discrimination index for that scale, they'll discriminate too. Now, if it's a strong negative loading, don't throw it out. If it's a negative 0.80, negative 0.48, negative 0.53, you keep that item. We can recode it. We'll just go back and tell the computer to, change the 7 to a 1 and the 1 to a 7, etc. That's what you can recode. And it'll do it automatically. These computers have created magic, almost. At least the software programs. Okay, I'm going to share something that John Wilder Tukey I mentioned to you. The word software, John Wilder Tukey. The word bits, John Wilder Tukey. The underlying mathematics that makes your computer run, fast Fourier analysis, Fourier mathematics, John Wilder Tukey. He didn't care anything about computers. He was a leading theoretical mathematical statistician. He developed exploratory data analysis, but also many of the multiple comparisons and robust methods of data analysis. He was a theoretical mathematical statistician. Interesting person. One time we asked him, had a class of 6 of us, he was a very humble person. And he said, we asked him, you're so humble, but in the world, you're theoretical mathematical statistics, you're the leading person in the world. And what he's done, the work he's contributed will be read 500 years from now. And he says back to us, what else can you be given our massive ignorance, he says. He says, the applied bodily knowledge is very thin. The basic or pure, the theoretical bodies of knowledge are very thin. But in all fields and disciplines. But he says, at least we know we don't know. So, yeah, remarkable human being. So I'll see you next week then.